Okay, good afternoon, my dear students. My name is Dr. K.C.H. Apparao, working as a associate professor in mechanical department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous class we discussed the rate of heat transfer through hollow cylinder and rate of heat transfer through coaxial cylinders or composite cylinders, and we also derived the formulas regarding the cylinder rate of heat transfer in cylinders, just like 2 pi kl into T1 minus T2 by ln r naught by Ra. So this was already derived in previous class. Also derived the rate of heat transfer for the composite cylinders. Okay, so that formula also derived in previous class. Also we discussed the critical radius of initiation in cylinders. So this one also explained in previous class. Now we'll see the heat conduction through hollow and the composite spheres. Okay. So we discussed the first of all we discussed the rate of heat transfer in the slabs and composite slabs. Next, rate of heat transfer in the spheres, no cylinders and composite cylinders. Now we'll see the rate of heat transfer through hollow sphere and the rate of heat transfer through composite spheres. Okay, we'll see. We know that in previous class we derived the general heat conduction equation through uh, spherical coordinate system. You know that we already derived this formula. So we'll see the heat conduction through the hollow sphere first of all. So this formula was already derived in previous class, this derivation. So this is the we know that spherical means it has three-dimensional body. So this is the formula with respect to dr r sin theta and d pi r d pi. So with respect to these things, so we derived the formula here. Okay. So here in this one, so this is the formula up to with respect to r. So this is the with respect to pi, and so this one is the with respect to theta. So this is the formula, and q by k, you know that heat generation in the small elemental area, and rho cp by k and dou t by dx. So this shows the steady state condition related formula. So rho cp by k, you know that 1 by alpha. Alpha is nothing but thermal diffusivity. So all these things were discussed in the previous class. Now we'll see for the derivation of the rate of heat transfer through the hollow sphere. So first of all, we'll see the just to take the small uh, hollow sphere. This is the three-dimensional shape of the hollow sphere. We can see this is the inner radius, so we can say that is the Ri, and the outer radius, so that R naught we can take. Okay, so here for the derivation of heat transfer rate for the small elemental area, so you can take that small elemental area. So this one is the small elemental area. So just thickness of the small elemental area is equal to dr, and the distance from the center point you can take that is the r. Okay, so this is the three-dimensional body. You can see the 2D body. Okay, so this is the center point of the sphere. So this one is the r1, is the inner radius of the sphere, hollow sphere, and the r naught is the outer radius of the hollow sphere, and the corresponding temperature, you know that so at Ri, so that is the Ti is the temperature, so inner temperature of the sphere, and the T naught is the outer temperature of the sphere. So for the calculation of the temperature and any particular radius, so for finding temperature T at any particular radius, so for that for solving that one, just take small elemental area which is shown by red color. So that is the radius from the center point, that is the r. This one is the r. Okay, so thickness of the small elemental area is equal to dr as shown here. Okay, so now q shows the heat flow, rate of heat flow. So we have to find out that one. So k shows the thermal conductivity of this solid material. So it shows this is the hollow sphere, you know that. Now we'll see that. So here only here we are considering the just rate of heat transfer with respect to radius, not considering the theta, not considering the pi. So it means it shows the unidirectional heat flow. It means one dimensional heat flow. So that which is in radial direction. It means with respect to r only. So for that one, just you have to take this term only. So okay. So you know that if you if we take some cases, the case one is the if this equation is in or it is in steady state condition. First one is steady state condition. Then you know that then temperature difference with respect to time, it will be 0. Then this total term will be 0. Okay, so that is the case 1. Case 2, if the heat generation is neglected, if we neglect the heat generation in the small elemental area, this small elemental area, then q by k, so heat flux by thermal conductivity, this will be 0. Then the formula will be like this one. It means dou by 1 by r square into dou by dou r into r square, so dou t by dou r plus 1 by r square into dou square t by sin square theta d pi square. So plus dou by r square, so sin theta d theta into sin theta dou t by dou theta, so equal to 0. So this total term will be equal to 0. So here we are considering only this one. It means unidirectional heat flow. It means one dimensional, we are taking the one dimensional with respect to r. No need to considering the theta, no need to considering the pi. So if you consider all these things, that is the 3D model. Just we are taking the one dimensional, so that is the radial direction. So you can take this term. So if this term plus this term plus this term is equal to 0, you know that then automatically dou by, so dou by r square into dou r of r square dou t by dou r, so it will be 0. So because total term is equal to 0, it means this term, this small portion also will be 0. So take this one small portion. So based upon this condition, it means unidirectional heat flow in radial direction. So take this small term. So it means dou by r square into dou r, or 1 by r square dou by dou r of r square dou t by dou r is equal to 0. You know that if it is 0, automatically 1 by r square will be 0. So then the formula is equal to dou by dou r of r square, so dou t by dou r is equal to 0. So integral both sides, integral here, integral here. Then the integral, if you integral this one, then integral and dou by dou r, so will be cancelled. So r square into dou t by dou r is equal to integral 0 means you can take that is a constant one, c1. Then send this r to that side, then dou t by, so dou r is equal to 1 by r square c1, or c1 by r square. Okay, you can send this dou r also. Then dou t is equal to dou r by, so r square into c1. Okay, so this is the two terms, dou r by r square and c1. Okay, integral both sides here and here. So integral dou t, it means that is the t is equal to integral dr by r square into c1. So you can apply the uv method. Then integral um, dou r by 1 by r square means, so we'll get the just minus 1 by r, so into c1, so plus c2. So this is the, it means so t is equal to the finally, so t is equal to, so we got this one after integration. So t is equal to minus c1 by r plus c2. So it is called general equation. So we know that's the same principle which was explained in the previous topics, which are related to spheres and no cylinders, and which are related to um, slabs also. So this is the general equation. You can see PPT also follow this one. So it means, so we finalize that one. So t is equal to minus c1 by r plus c2. So this is called general equation. Now we consider the boundary conditions for this one. You know that the boundary conditions. So first boundary condition, if r is equal to ri, then temperature T is equal to Ta. That is the first boundary condition. If r is equal to r naught, then temperature is equal to T naught. There are two boundary conditions. You can consider this one. If T is equal to Ta, then r is equal to ri. Or if T is equal to T naught, then r is equal to r naught. Okay, so these are the two boundary conditions. By using the boundary conditions, find the C1 and C2 values. After finding the C1 and C2 values, you can substitute these C1 and C2 values in the general equation. Then you will get the temperature formula. Okay, so okay, apply the first boundary condition in the general equation. Here, just like we apply the first boundary condition, it means if T is equal to Ti, R is equal to Ri. So it means at the place of the T, you can put the Ti. So Ti is equal to minus C1 by Ri plus C2. So that is the first equation. So if you apply the second boundary condition, so boundary condition 2, so T is equal to T naught, R is equal to R naught. If R is equal to R naught, T is equal to T naught. So that is the T naught is equal to minus C1 by R naught plus C2. That is the equation 2. So these two equations, if you subtract the equation 2 from the equation 1, so subtract the equation 1 from the equation 2, it means this is the minus, this will be plus, so this will be minus. So plus C2 and minus C2 will be cancelled. Then so in this one, so minus C1 by Ri plus C1 by Ri, you can take this C1 common, then 1 by R naught minus 1 by Ri is equal to Ti minus T naught. So from this one you will get the C1. So C1 is equal to Ti minus T naught by 1 by R naught minus 1 by Ri. So this is the C1 value. Then by using the C1 value, you can find out the C2 value. C2 value. If you substitute the C1 value in any equations, equation 1 or equation 2, you will get the C2 value. Okay. After finding the C1 and C2, you can substitute these C1 and C2 values in T. You will get the T value. Okay. Okay. So you know that just here we are taking the equation 1. So that is the Ti is equal to minus C1 by Ri plus C2. So from which, so we will find the constant C2. So then constant C2 is equal to, so we can send this one, so another direction, another side. So then C2 is equal to Ti plus C1 by Ri. You know that C1 value. So and previous one, that T1 C1 is equal to, you know that, so Ti minus T naught by 1 by R naught minus 1 by Ri. Okay, substitute this value in the place of C1. Then C2 is equal to Ti plus Ti minus T naught by 1 by R naught minus 1 by Ri plus Ra. So this is the C2 value. Then you can put these C1 and C2 values in the general equation. You know that so substitute the C1 and C2 values in general equation. We know that the general equation T is equal to minus C1 by R plus C2. So if you apply C1 and C2 values in general equation, then we will get the temperature at particular radius R for the small elemental area. Okay. So this is the substitution. So you know that too. So this is the general equation. So T is equal to minus C1 by R plus C2. So then substitute the C1 and C2 values. You know that C1 value and the the C2 value also. Okay. So then the formula will be like this one. So in this term, Ti minus T naught by 1 by R naught minus 1 by Ri, here also there and here also there. You can take the common the term. So, and this is the minus, this is the plus Ti. So you can write Ti initially and take Ti minus T naught by 1 by R naught minus 1 by Ri. So you can take the common term. So the remaining term is equal to 1 by R. So that is minus 1 by R. Okay. Here 1 by Ri. So this is the positive 1 by Ri. This is the negative 1 by R. So then you can write like this 1 by Ri minus 1 by R. So this is the formula for the finding of the temperature at particular R. So in the sphere, if it is a hollow sphere, if you want to find the temperature at particular region, so this is the region is equal to R distance, the temperature is equal to T. So you can find the temperature value at particular radius, at any particular radius, by using the boundary condition, initial boundary condition and final boundary condition, or boundary condition 1 and boundary condition 2. So this is the T formula. Just remember this one. Now we'll find the just like rate of heat transfer in the hollow sphere. So for this one, you know the conduction formula. So you know the Fourier's law. So this is the temperature T already derived in previous slide. So you know that conduction formula. So not conduction. This is the Fourier's law with respect to R. Okay, minus Ka dt by dr. Okay. So you can rewrite like this one. So you know that minus K into area. Area for the small elemental area. You have taken, this is the hollow sphere. So you have taken small elemental area here at particular distance. Not good. This is the hollow sphere. Okay. So I have taken this small elemental area. This is the small elemental area. So you know that this is the Ri inner radius. This is the R naught outer radius. This is the R particular radius. So that is the R. Okay. So now that for the small elemental areas, the area of the small elemental area, that is the, so you know that area of the that element, it means this particular region. So you know you can write the formula for the area of spheres, that is the 4 pi r square. Okay, you can write area is equal to 4 pi r square minus k. K is the thermal conductivity of the this sphere material. Next d by dr into t. So that is the capital T. So T is nothing but this one. Okay, so you can substitute this total term in this one, then we will get the rate of heat transfer in the small elemental area, hollow sphere. So rate of heat transfer in this hollow sphere. So substitute the value of T in this one. You can observe like this one. So here T is equal to, so Ti plus Ti minus T naught by 1 by r naught minus 1 by ri into 1 by ri minus 1 by r. So this is the t value substituted. Okay, so we can derivative with respect to r. So we can derivative this total term with respect to r here. So only r is here, so we can derivative this one with respect to r. Okay, so then the formula will be like this one. If you derivative this one, you will get this one, so minus k into area and d by dr. So derivative of this one means ta is the constant with respect to r, so this will be 0. And so here 1 by r is the constant, 1 by ri, so it is the constant with respect to r. So then this is the 1 by r, we have to derive with respect to r to 1 by r. So then the formula is uh, will be like this one. It means so ti minus t naught by 1 by r naught minus 1 by is the common term. Okay, so here minus is there already, minus is there, you can write minus. And so derivative of 1 by r, so derivative of 1 by r is equal to that minus 1 by r square. So you know the value, so this is the minus 1 by r square, so minus of minus 1 by r square. So then the formula will be like this one. It means so here r square will be cancelled, minus into minus plus. Next here also minus is there. To cancel that minus, just we are rearranging this one. So it means 1 by r naught minus 1 by ri, just to have written 1 by ri minus 1 by r naught. So if you take common, minus minus will be cancelled. So this is the final formula. Okay, so it means q is the rate of heat transfer through hollow sphere. So we already derived rate of heat transfer in this slab, single slab, rate of heat transfer in hollow cylinders we derived, and rate of heat transfer in hollow sphere. So this is the formula. So these three formulas you have to remember that one for the solving of different numericals based upon the slab, cylinder, and the spheres also. Okay, this is the formula. We can rewrite like this one also. So Q is equal to 4 pi k into ti minus t naught by. So here if you take common LCM, just like r naught ri, so this will be r naught minus ri. Okay, you can rewrite like this one, just like q is equal to 4 pi k into r naught ri into ti minus t naught by r naught minus ri. Okay. So you can rewrite like this. Okay, so you can remember this one, this formula like anyone. So here also I given these formulas in PPT. You can observe like this one. So this is the formulas. So Q is equal to finally 4 pi k into ri r naught or r naught ri into ta minus t naught by r naught minus ra. You can rewrite like this one. And also you can rewrite like this one also. You know that Q is equal to delta T by thermal resistivity formulas. Okay, so it means so r naught minus ra by 4 pi k into ri r naught. So this is the formula. Okay, just remember these formulas. So now we'll see the rate of heat transfer in the composite spheres. It means if you consider the more layers in the sphere. Okay, so this is the just like small diagram. So here two layers of this sphere has been taken. So layer 1 and layer 2. Okay, so inner diameter of the sphere. So that is the, here we are taking the r1. Okay, next if you add this thickness of the first layer, you will get the r2. R2 is nothing but r1 plus thickness of first layer, layer 1 thickness. Okay, so then the r3. So this is the r3 is nothing but just r2 plus thickness of layer 2. Okay, So in this way, you can find out the radius of uh, uh, so different layers. Okay, so R1 is the hollow diameter radius. Next, R1 is the outside of the radius of outside radius of the layer 1, and R2 is the outside layer of the layer 2 up to layer 2. So also you have to consider the, if you assume that there is a heat gas or the gas in the hollow space, so then you can consider the um, rate of heat transfer for the gas hollow space which is placed in the hollow space. So that is the, you can take hot fluid heat transfer coefficient of hot fluid, or you can take HA, inside is the A, or you can represent this one hot fluid uh, rate of heat transfer of the hot fluid. Okay, so outside, so you can take that is the rate of heat transfer of the cold fluid. So according to so discussion the previous classes, otherwise you can take HB is the outside of the rate of heat transfer. Okay, so next to temperatures you can assume that one. So inner temperature, the temperature of the hot fluid you can take represent like this one, or otherwise you can represent Ta. Ta is the inner fluid temperature, and Tb is the outer fluid temperature, it means cold air, atmospheric air, or we can represent like this one, T uh, cold fluid. Also we can represent like this one, T infinity 1 or T infinity 2, like this one. So you can represent any one parameters, don't confuse that one. So try to understand this one. So these are the just like parameters. So you can observe. Now we'll see. So here heat transfer rate, heat transfer it takes is from the, so inner gas, first of all fluid gas to inner surface of the first layer. Okay, it means, so it means temperature, hot fluid temperature to uh, inner layer temperature of the first layer, that is the temperature T1. Okay, so next to, so heat transfer takes place from the inner layer temperature T1 to just inner layer temperature of the T2, that is the temperature T2. So it means, so this one is the T1. So Ta or THF shows the hot gas temperature, and T1 shows the inner layer of the layer 1. Okay, so T2 shows the intermediate between the layer 1 and layer 2, or outer radius of the layer 1 or inner radius of the layer 2. So that is the temperature T2, and T3 shows the outer radius temperature, so of the layer 2. So that is the T3. So it means, so next to T2 to T3, this is the T3. Next 3 T3 to TB or TCF, cold fluid. Okay, so it means, so first of all hot fluid to solid. So that means, through convection principle, convection process, heat transfer takes place. So this is the by convection process. Next in layer 1 heat transfer in layer 1, so it means temperature 1 to temperature 2. So this is the conduction, so because of solid, through conduction process. Okay, next to layer heat transfer in the layer 2. So this one, it means T2 to T3. So that one also through conduction process. Next to last to outside temperature T3 to atmospheric air. So that is the TB or CF, cold fluid temperature. So that is the it means solid to fluid means convection process. So finally heat transfer takes place by two modes. The first one is the convection mode. Next to conduction mode, convection mode. So you can represent that one. So uh, so here also we can represent like this one: thermal resistivity of convection one, thermal resistivity of the conduction one. Okay, so we'll see, so that the just like electrical analog formula we'll see later. So these are the processes. So finally heat transfer takes place by here two modes. The first one is the convection. It means inside hot fluid to inside layer uh, layer of the inside surface of the first layer. Okay, so we'll see one by one. So heat conduction through hollow composite spheres, we'll find this one. So first we'll take the condition one. So rate of heat transfer from the hot fluid to inner surface, it means THF to T1 heat transfer rate. Okay, so this is done by, so because heat transfer uh, takes place from the liquid to solid. So it means through convection principle, just the heat transfer takes place. You know the formula for the convection, that is the Q is equal to HA into temperature difference. You know that formula. So here H is nothing but H with respect to hot gas. So that is HF, hot fluid, rate of heat transfer into area of the, so inner surface, that is the, you know, that radius of hollow, that is the R1. So then, so area of the sphere is equal to 4 pi R1 square. Okay, so next to temperature means hot fluid temperature to inner temperature of the layer. So layer 1, it means, so THF minus T1. Okay, so this is the formula. So Q is equal to rate of heat transfer of the hot fluid into area, inner surface area of the sphere, 4 pi R1 square into temperature differences. Okay, so you can rewrite like this one. So temperatures THF minus T1 is equal to, so Q by HF hot fluid into 4 pi R1 square. Like this one, you can take, this is the equation one. Okay. Otherwise, if you have any confusions, take this is the HA. Inner means A, outer means B. You can represent like this one. No need to worry about this one. Okay. So then inner temperature TA and outer temperature is equal to TB. So you can represent like this one. Okay. So this is the just like formula 1 through convection principle. It means heat transfer from the hot fluid to inner surface of the layer 1. Inner surface of the layer 1. Here, just I am giving the formula here. You can see this one. Okay. So Q is equal to HA, just to, or H hot fluid, HF, you can write like this one also, into 4 pi R1 square. So inner space, radius of the inner space is equal to R1. So 4 pi R1 square into temperature differences. So TA minus T1 or THF minus T1, you can write like this one. Then temperature TA minus, sorry, so TA minus T1. So TA minus T1 is equal to Q by HA into 4 pi R1 square. So this is the formula 1. Okay. So next we'll see the, so here transfer, this is the convection principle, rate of heat transfer takes place. Then the conduction principle, it means rate of heat transfer in the layer 1. So we'll see that one. Okay, rate of heat transfer in the inner surface, it means layer 1. Okay, so you know the temperature, so T1 to T2. Okay, temperature decreases from the temperature 1 to T1 to T2. So you know the formula for the conduction, that is the, just was we derived in the previous slides, that is Q is equal to 4 pi, just to radius is equal to R1 and R2. So R1 R2 into temperature differences. Temperature is equal to T1 minus T2 by, so R2 minus R1. So this is the formula. Okay. So next you can rewrite like this one, just like T1 minus T2 is equal to Q into, or Q by, you can write like this one, uh, Q by 4 pi R1 R2 by R2 minus R1, like this. So this is the uh, equation 2. You can consider this is the equation 2. Okay, just in PPT you can observe this formula like this one. Okay, so this is the equation 2. It means the rate of heat transfer in the layer 1. Okay, first of all, hot fluid to inner surface of the layer 1. Next to heat transfer in the layer 1. Okay, so this is the formula. We got the two equations. Now heat transfer in the layer 2, it means the temperature T2 to T3. We'll see that one. You can read it like this. This is the rate of heat transfer from inner surface of the inner layer of, it means you can write directly heat transfer in the layer 2. Layer 2. Layer 2. It means temperature T2 to T3. Okay, so radius is equal to, this is T2, this R2, this is R3. Okay, you can just the formula. So then Q is equal to 4 pi thermal conductivity. So we forgot that thermal conductivity. So K1 is the thermal conductivity of the layer 1. So next to 4 pi K2, so thermal conductivity of the layer 2 into, so radiuses, so that is the R2 and R3, and temperature differences T3 minus T2 minus T3 divided by R3 minus R2. So this is the formula. Okay, so then you can rewrite like this one, T2 minus T3 is equal to Q by 4 pi K2 R2 R3 by R3 minus R2. You can rewrite like this one. So this is the equation 2. Just you can observe in PPT. Just a printed matter. So this is the equation 3. Okay, you got the equation 1 to equation 2, equation 3. Okay, so heat transfer takes place up to the outer surface of the layer 2. Now we'll see the heat transfer from the outer surface of the layer 2 to ambient temperature. It means atmospheric temperature, cool fluid temperature. Okay, so that is done by, it means solid to liquid. So no, solid to fluid. So that is the convection process. By using the convection process, you can write the rate of heat transfer. Okay, the rate of heat transfer from the outer surface of the layer 2 to atmospheric conditions. Okay, atmospheric conditions. It means temperature T3 to T cool fluid. Otherwise, you can write to TB. Okay, or T infinity to, you can write anything. So then the formula based upon the, that convection process, the formula is equal to HA into delta T. So H is related to cold fluid. It means HB you can write, or H cold fluid you can write. So rate of heat transfer with respect to cold fluid. No. Rate of heat transfer of the cold fluid. Okay. Or rate of heat transfer of the cold fluid. You can represent HCF or HB. Anything. Next to area. So area, outer radius with respect to R3 how to write. So outer radius to outer surface to atmospheric conditions. So you have to consider R3. So then the formula is equal to 4 pi R3 square into, so temperature differences, that is the temperature differences is equal to T3 minus TB. You can write it. TB is nothing but TCM, cold fluid temperature. Okay, so this is the formula. Then you can rewrite the formulas. T3 minus TB is equal to Q by, so HB into 4 pi r3 square. So this is the formula. This is the equation 4. Okay. So we got the finally 4 equations. Then you can add the equation 4 equations. Equation 1, equation 2, equation 3 and equation 4. So this is the equation 4. If you add the equations, you will get like this one. Just once again I'm repeating this one. If you add equation 1 plus equation 2 plus equation 3 plus equation 4. Okay. So first equation means TA minus T1 is equal to so Q by so left side terms and right side terms. Just I am adding all the left side terms. TA minus T1 plus T1 minus T2 plus T2 minus T3 plus T3 minus TB. Okay. So minus T1 plus T1 will be cancelled. Minus T2 plus T2 will be cancelled. Minus T3 plus T3 will be cancelled. The finally left side terms is equal to TA minus TB. So initial temperature minus final temperature is equal to. So just like right side terms you can add. What is the first term is equal to Q by HA into 4 pi R1 square plus so second terms 4 pi so Q by 4 pi K1 into R1 R2 by R2 minus R1. So this is the second equation. So plus Q by 4 pi K2 R2 R3 by R3 minus R2. This is the equation from 3. Then fourth equation. So Q by HB into 4 pi R3 square. Okay. So in this total terms Q by 4 pi. So this is the common term. You can common. You can take the common for Q by 4 pi. So then this is the 1 by HA R1 square plus 1 by K1 R1 R2 by R2 minus R1 plus 1 by so K2 R2 R3 by R3 minus R2 plus 1 by HB R3 square. So this is the term. We got this one. Just we can observe like this one. This is the terms. The final formula is equal to. So it means here. So here this is the TA minus TB is equal to this one. So from by using just you can find the Q rate of heat transfer. Then Q is equal to 10. You can send all the terms 4 pi here and this one here. Then we'll get the final formula like this one. So Q is equal to 4 pi into so TA minus TB by 1 by HA R1 square plus R2 minus R1 by R1 R2 K1. Okay. So plus R3 minus R2 by R2 R3 K3 K2 plus 1 by HB R3 square. So this is the formula, final formula. So this is the formula for the rate of heat transfer in the composite spheres. So finally you derived the two formulas here. You have to remember that one. So rate of heat transfer in the hollow sphere. So that is the formula Q is equal to so 4 pi so K into Ri R naught into temperature so Ta minus T naught by R naught minus Ra. So this is the formula. Okay. So if you have many layers, it means so rate of heat transfer in the composite spheres. So just like you have taken two layers, so then the formula will be like this one. Okay. So these two derivations are very important. We have to remember this one. So we can rewrite this formula like this one. Okay, so it means q is equal to 4 pi ta minus tb by 1 by ha r1 square plus 1 by hb rn plus 1 square. If you, it means n is the number of layers. Okay, here number of layers. Okay, so here just like I'm taking the, we have taken the n is equal to 2, then the formula is equal to, it means so rn plus 1 means r3 square, like this one. If you take more number of layers, you can use this general formula for finding the rate of heat transfer in the composite spheres. Okay, so this is the formula. So rn plus 1 minus rn by rn into rn plus 1 into kn. K is the number of layers. Okay, so this is the formula. You have to remember this one. Now we'll see the electrical analog. How to write the electrical analog formula? You know that electrical analog formula means this is the voltage and the resistance, and this is the voltage V1 V2. But here temperatures, thermal differences means this is the T1, this is the T2. Okay, so it shows the thermal resistivities RTH. So then you know that formula. So I is equal to V by R. So based upon the Q is equal to temperature differences. So delta T by RTH, thermal resistivity. So this is the formula. We can use this type of the formulas to solve these problems easily, to understand the problems easily. Okay, so okay, by using this electrical analog process, we can rewrite this previous formula, this formula. So this formula we can rewrite like this one. Just see how to write easily by using the electrical analog formulas. Okay, just to explain this one. T8, T2 are sphere, thermal resistivity of the sphere. Sphere means so that is the solid. It means thermal resistivity with respect to conduction process. So here we have two types of the modes are used uh, to transfer the heat. Okay, that is the one is the convection, another one is the conduction. So thermal resistivity with respect to convection process, thermal resistivity with respect to conduction process. You can write conduction or we can write sphere. So because it is the sphere. Okay, so here just like we can write like this one. So here just like we are using the electrical analog formula for the composite spheres. Okay, here inner fluid, that is you know that temperature of the hot fluid. Next to temperature, inner layer, there are two layers, just according to previous one, layer 1 and layer 2. So it means temperature of the inner layer temperature T1, outer layer temperature of the T2. So outer layer temperature of the layer 2, that is T3. So hot fluid temperature to T1, T1 to T2, T2 to T3, next T3 to cool fluid, atmospheric conditions, that is the TCF. You know that one. Okay, so then the formula is like this one. So heat transfer from the hot fluid temperature to temperature 1. So that is the convection process. Just we can take the thermal resistivity with respect to convection. Okay. So next to T1 to T2. So temperature T1 to T2, it means inner temperature of the layer 1 and outer temperature of the layer 1. So that is the, so that shows the represents the heat transfer in the layer 1. Okay, so that means we can take that is the R1. Okay, so R1 means the means thermal conductivity of the layer 1. R2 shows the thermal resistivity of the layer 2. So next to So this is the thermal resistivity of the layer 2. Next to outside temperature of the layer 2 to ambient temperature at atmospheric temperature, that is a T cool fluid. You can take, or we can take TB, or you can show T alpha to infinity to, okay, T infinity to. So you can represent like this one. So that is done by, it means so heat transfer from the solid to fluid. So that is the convection process. See here there are two convections, R convection 1, R convection 2, and two conduction process. So basically there are two modes here uh, to transfer the heat from the inner fluid to outer cold fluid, rate of heat transfer. So you can rewrite the formula like this one. It means uh, so according to formulas, that is the rate of heat transfer is equal to temperature differences. It means delta T overall. Overall means initial temperature, final temperature by the sigma x, sigma r. Sigma r means the total thermal resistivity. Thermal resistivity means this is the R convection 1 plus R1 plus R2 plus and R convection 2. Okay, thermal resistivity. So it means temperature difference by all thermal resistivity. You can write like this: thermal resistivity of the convection 1. You know that that is the R1 is equal to, according to the previous one. So this is the R1. This is the R2. So this is the R3. Okay, so R1, R2. This is the just like convection 3. Okay, you can rewrite like this one. R1 is equal to 1 by HA or HCF. You can write like this one: HA R1 square. So that is the uh, thermal resistivity 4 pi HA. We have to write 4 pi R1 square into HA. Okay. So because 4 pi is the common term, you can take like this one. So, write commonly. Next to just to R convection. R convection 2, I am writing R convection 2 is equal to 1 by 4 pi R3 square. R3 square outer radius into HB square. Not HB square, HB. Okay. So this is the thermal resistivity of the R convection. So remaining R1 and R2 just also I am mentioning like that one. R1 is equal to, so R1 is equal to, you know the formula for this one, that is Q is equal to 4 pi R1 R2 thermal conductivity is T1 minus T2 by R2 minus R1. This is the formula. So you can send like this one. So that is the temperature by something. So that is the thermal resistivity. It means T1 by T2 is equal to R2 minus R1 by, so 4 pi K into R1 R2. So this is the thermal resistivity. It means R1 is equal to R2 minus R1 by 4 pi K R1 R2. So this is the thermal resistivity of layer 1. Similarly, thermal resistivity of the layer 2 is equal to R3 minus R2 by 4 pi K2 into R2 R3. So the thermal resistivity of the layer 2. So you can add all these things individually, you can find out and you can solve the formula directly easily. So it means Q is equal to delta T. It means initial and final temperatures by sigma R. You can add all the thermal resistivity. So by using this electric and analog formula, we can solve the numericals easily. So that is the benefit of that one. Now another concept is the overall heat transfer coefficient. So this is also very important to term. You know that the heat flow rate Q through multi-layer sphere. So it can be expressed like this one: Q is equal to UA delta T is the common term, UA delta T. So if you consider this one inner surface and the outer surface, it means one represents the inner surface and two represents the outer surface. Rate of heat transfer with respect to inner surface, that is the formula, is equal to U1 A1 into delta T. Similarly, rate of heat transfer with respect to surface 2, that is U2 A2 is equal to delta T. Okay, so you can rewrite like this one. So U is the overall heat transfer coefficient. You have to remember this one. Sometimes these questions find the overall heat transfer coefficient in this. Uh, you will be asked in the numericals to solve the overall heat transfer coefficient. Okay. So you can rewrite like this. It means you know the formula Q is equal to U delta T by thermal resistivity sigma RTH. So it means thermal. So U1 A1 is equal to U2 A2 is equal to 1 by sigma RTH. Okay. So total thermal resistivities, reciprocation of the total thermal resistivities, that is called U1 A1. Okay. So then you can find out anything just like U1 is equal to 1 by A1 into sigma RTH, or U2 is equal to 1 by A2 into sigma RTH. So in this way you can find out the overall heat transfer coefficient. Okay. So U1 is with respect to inner surface, U2 with respect to outer surface. Now we'll see the critical radius of insulation on the sphere. We already discussed the critical radius of insulation in the cylinders also. Okay. So same process we have to use here also. For this one, just we are considering a small hollow sphere of radius R1. So is covered with a layer of insulation. So that is the, it means hollow sphere, and so that is the hollow sphere is covered with the insulating material. So this is the insulating material. Okay. So thermal conductivity of the solid, that is a K. Thermal conductivity of not just we are taking the thermal conductivity of the insulating material, because we have to find out the critical radius of insulation. So insulation material thermal conductivity how to consider. Okay. So it means here heat transfer takes place by the hollow sphere to next to insulation. So in the insulation, heat transfer takes place by the conduction process. Next to outer insulation materials to atmospheric air. So that is the convection principles. So convection mode. It means heat transfer takes place in the insulation. No need to consider the solid sphere, another sphere. Consider the insulating material. So next to outer rate of heat transfer from the insulating to atmospheric conditions. So the heat transfer takes place by, one is conduction, next one is the convection. Okay. So we'll see like this one. So you can observe the diagram like this one. So this is the inner, that is the hollow sphere. There is a hollowness is there, no need to consider this one. Okay. So we are taking the outer radius of the sphere is equal to R1. It means inner radius of the insulating material, that is the, so next outer radius of the insulating material, that is the R2. R1 is the inner radius of insulating material, and R2 is the outer radius of the insulating material. We are considering only insulation layer. So rate of heat transfer in insulating material through conduction. So that is the formula, that is the R2 minus R1 by, this is the thermal resistivity of conduction. Okay. So 4 pi thermal K, the thermal conductivity of the insulating material into radiuses R1 and R2. Okay. Next process is the convection process. It means outside of insulating to atmospheric air condition. So that is the formula, you know that. So 1 by 4 pi r2 square into h b you can take, or here there is no h ha, so we can take right directly h. Okay, so it means so this is the conduction, this one is the convection. Okay, heat transfer is takes place. Then the final formula is equal to, you know that based upon the electrical analog, so q is equal to delta t by sigma r. Okay, so r means conduction and r convection is there. Okay, you can write like this one. So the initial temperature is equal to T1 and to TB, you can take like this one. It means our T cold fluid temperature, TCF, you can write like this one. So then the formula will be like this one. So you can, final formula is equal to like this one, you can see this is the final formula. So Q is equal to rate of heat transfer is equal to temperature T1 to, so T1 is the temperature of the inner surface of the insulating layer. No need to consider the uh, inner inner sphere. So we are considering only the insulation material, because we have to find out the critical radius of insulation. Then T1 minus TCF. So TCF is the cold fluid temperature by, so this is the convection radiance, thermal resistivity of the conduction. This is the thermal resistivity of the convection. It means so R2 minus R1 by 4 pi R1 R2 K. So 1 by 4 pi R2 square into H. Okay. So this is the value. You know that this one, this topic also covered, already explained in the cylinders. Okay. So because for the slab, if you add the insulating material, automatically rate of heat transfer will be decreases rapidly. But in case of spheres and cylinders, initially if you add the insulating material, initially it will increases, rate of heat transfer increases at particular time, it will be maximum, then rate of heat transfer completely decreases. Okay, so this maximum point, that is called critical radius of insulation, RCR. Okay, already this topic is covered in the previous classes. Okay, in mainly in the critical radius of insulation in cylinders. Okay, so here critical radius is equal to, it means so R2 will be maximum, R2 will be maximum and particular condition. So it means so at particular R2 value, the rate of heat transfer will be maximum. So sorry, this one. So at particular R2 value, the rate of heat transfer Q is maximum. So after that, the rate of heat transfer does not increases, that decreases. It means at particular radius. So at particular radius R2, Q is maximum. Q maximum means so dq by dr2, so it will be 0. It means so it means dq does not change with respect to r2 at the particular maximum point. So we have to consider this one. So you can derivative this one, dq by dr2 is equal to 0 for finding the r2 critical radius of the r2 value. Okay, so if you solve this one, so this was you know that u by v method derivative. So if you solve this one, you will get the final formula, that R2 is equal to, or RCR, it means critical radius of insulation, is equal to 2K by H. You have to remember this formula. Okay, so in case of cylinders, so this critical radius of insulation is equal to only K by H. So that is the formula for the cylinders. But in case of spheres, critical radius of insulation is equal to 2K by H. We have to identify the differences between the critical radius value for the cylinders and the spheres. Okay, so this is the one more topic. Okay, now we'll see the one numerical based upon the rate of heat transfer and in single sphere. So you know that we already find that formula. So P is equal to 4 pi K into Ri R naught into temperature T1 minus T2 by R naught minus Ri. This is the formula already derived this one. So based upon this formula, we will solve this numerical. Okay, just read this numerical and understand the data what is given in this numerical. Okay, a spherical thin-walled metallic container is used to store liquid nitrogen. So in the hollow space, so this is filled with nitrogen gas. Okay, the temperature of that gas, T hot fluid, so that is 77 Kelvin. The container has the diameter. So this container diameter is equal to 0.5 meters. Okay, so small d1 is equal to 0.5 meters. So r1 is equal to 0.25 meters. Okay, so is covered with evacuated reflective insulating system composite of silica powder. Okay, so this cylinder is covered with the insulating material which is made by the silica powder. So this is the layer thickness is equal to that one, so given 25 mm. 25 mm. So 25 mm means convert into meters. Then radius of insulating material, outer radius of the insulating material, that is the R2. Okay, R naught you can take. Otherwise, this is the Ri, this is the R naught you can take like this one. R naught is equal to Ri plus thickness of insulating material. Insulating material. It means Ri plus insulating material is equal to 25 mm converted to meters. It is equal to 0.025. Okay. So then R2 is equal to 0.275. Okay. So you got the R1 and R2 values. Next insulating thermal conductivity K also given. K is equal to 0.0017 watt per meter Kelvin. Next it is exposed to ambient air temperature. Outside temperature, that is the, so here outside temperature is equal to high, inside nitrogen temperature is equal to low. So you can rewrite like this one. So nitrogen temperature, it is a cold fluid temperature. So ambient temperature, that is the hot fluid temperature, because heat always transfer from the higher temperature to lower temperature. So hot fluid temperature is equal to 300 Kelvin. Okay. So next the convective heat transfer, it means this ambient temperature, air temperature, H value, heat transfer coefficient of cold fluid. Cold fluid means here hot fluid, or H, because there is no another fluid. You can take H is equal to 20 watt per meter square Kelvin. So all the parameters, K given, H given, R1, R2, you know that values. Then substitute the values. Okay. So this is the process. We can understand like this one. So this is the given data. Once again, I am repeating. This is the given data. R1 is equal to T given. So diameter is given. So we can find out the radius. Next, R2 is equal to R1 plus thickness of the insulating material. That is the 0.275. So thermal conductivity of the insulation also given. Okay. Next, ambient temperature, convective heat transfer coefficient of ambient temperature, HO. You can take HO or HF, and you can take. So that is the 20 watts per meter square Kelvin. Okay. So cold fluid temperature, you can rewrite like this. This is not a cold fluid. You can take, this is a hot fluid. This is the cold. Okay. No. Right. So this is the cold fluid, which is small, that is a cold fluid, which is high temperature, that is the hot fluid you can take. Okay. So then you can solve this one. You know that formulas here, one is the conduction is taking place, another one is the convection is taking place. Okay. So it means, so from insulation, that is the conduction, from insulation to ambient temperature, that is the convection, or conduction or convection. Okay, our conduction formula is equal to thermal resistivity R2 minus R1 by 4 pi R1 R2 K, based upon the analog formula, electrical analog formula. Similarly, thermal resistivity of the convection base 1 by 4 pi R2 square into H naught. So these are the values. You can solve this one because substitute all the R2 and R1 and R1 R2 K values. You will get these values. Okay. Then the final formula, you know that Q is equal to delta T by sigma R. So delta T means initial and final temperature, hot fluid temperature minus cold fluid temperature divided by thermal resistivity or conduction plus R convection. Okay. So you know the value. So substitute all the values, you will get this one. This is the sample numerical to understand the concept. Next, we will see many numericals based upon the rate of heat transfer in the hollow cylinder sphere and the composite spheres also. So thank you for watching this class. We will continue the remaining topic in another class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.